Okay, welcome to lesson 45. So in the previous lessons, we walked through making a scatter plot and describing the scatter plot between two quantitative variables, fitting the least squares regression line and using it to make predictions. Now we're going to go ahead from beginning to end, go through an example with anglerfish. So first, we're going to go through our steps here. The first thing you want to do is describe the relationship between your two, in this case, quantitative variables. So quantitative response variable, quantitative explanatory. Graphically, you're going to use a scatter plot. So make sure that you have your explanatory on your x-axis, your response on your y, and then numerically, it is appropriate to use the correlation coefficient R if you have a linear relationship between the two. So calculate the least squares regression line in equation. That will be your next step. Go ahead, calculate your residuals, plot your residuals plot, and check your conditions for inference. You want to make sure that it was appropriate to fit a line, that the points are roughly normally distributed around that line, constant variance around the line, and independence. So for the QQ plot, you want to see random scatter. For the residual plot, you want to see random scatter. For the QQ, the normal plot, you're going to want to use it to see, hey, are these roughly normally distributed? So is your model a good fit? We're going to go ahead and look at the that t-test for the beta, see, hey, was it useful to use this explanatory variable to give us more information about what's going on with the response variable? You can interpret it, confidence interval, and then make predictions. Absolutely, confidence intervals, prediction intervals, maybe you want to know, hey, for a specific value of the explanatory, what do I estimate that the average is for all responses? Or what do I predict the response is for just a single new response? Always return and ask yourself, did I answer the question? It's really, really important. It's really easy to go off on a tangent in stats. Always make sure you answered the question. So here we have some scientists that are concerned that we have rising temperatures globally, and it is making several animals be found in different locations in the oceans. So they decided specifically to look at white anglerfish, data that's from 1977 to 2001. They also record the average winter temperature at the bottom of the North Sea in degrees Celsius, and we've put it into a scatter plot, and we want to talk about what it looks like. So, because you definitely don't want me to handwrite this much while sort of sounding it out, the relationship between average sea temperature and the anglerfish latitude looks to be moderately strong. Yeah, I would say reasonably. I definitely see a linear trend there. It's moderately strong with a correlation of 0.6. No, you can't figure that out by looking at it, but we did provide R code. You can find that correlation coefficient. So essentially what this is, I have a moderately strong positive linear relationship as average winter sea temperature increases in that North Sea. The latitude of the anglerfish also tends to increase. You want to be careful that you don't write it as increasing the temperature increases the latitude, because that's causal language. The relationship looks like it could be modeled with a straight line. Yeah, that seems reasonable. The scatter plot supports the assumption that increasing sea temperatures may increase the latitude anglerfish are found. Thing to note, we did mention we might have an outlier here. So there is an extreme value at approximately 6.3 degrees Celsius, so here, and 59 degrees. That should be investigated. So maybe find out, hey, what happened? What's going on with that point? Is it recorded accurately? Was it measured accurately? Just double check. So calculating the least squares regression line, run it into R, and they will have right there. So first things first, you can say y hat is equal to, I'm going to put my y-intercept, so 52.45. I'm going to only round to 2 places here. Always round to at least 2. Plus 0.82 times x. If I do it this way, I need to say y hat is my predicted latitude, because that's my response, and x is my average sea temp. So we will do this. We will go ahead, we will say, hey, write out your least squares regression line in notation. This is what we mean, and label in, if you label y hat and label x. Alternatively, you could also write latitude. Note this is grosser to type because the hat gets really wide. So you can say, put the hat over latitude is equal to 52.45 plus 0.82 times temp. That would be acceptable as well. Just make sure, it is important you still have that hat. So now we want to go ahead and check our conditions. Here's our residuals plot. We also made a histogram at the residuals. So is the relationship linear here? Was it appropriate to fit a line? So, oops. Looking here, I don't see any big curve shapes. I would say yes. It's so no curved, oops. No curve shape. I would say yes, it's met. Specifically looking at the residuals plot. The follow-up there, do they vary normally around the population regression line? So there will be a couple of ways. One way you can take those residuals and put them in a histogram, look at it and say, hey, the histogram looks approximately normal, so residuals histogram. This is not actually commonly the way that we do it, but it looks approximately normal. We usually use a normal QQ plot, which I will show you in the next slide. Normal. So, like, it would be reasonable to say, yeah, that's roughly normal. Are they independent? So this is going to say, as long as these observations are independent, if you're recording the same fish over and over, or if it's like a school, like maybe not, but oops, as long as unrelated observations. Yes. So, and sometimes in reality, like you can say, yeah, it seems reasonable they would be unrelated. Yes, as far as we're concerned, they did not take a random sample of anglerfish because that would be difficult to do. Random samples of any wild animal or even people are very, very difficult to obtain. So then our last question, so do we have that constant variance or constant standard deviation of the responses? So I'm looking at the residuals plot again. Here I'm looking for fanning out or funneling in, and roughly, I mean, this is an oddball point, but it seems pretty constant. It's not really fanning out, funneling in too much. So residuals plot. No fanning out. Funneling in. So yes, I would say this was met. That we have very constant variance, and that's why I'm saying, like, looking at here, that spread looks pretty consistent. Yes, there's one odd point, but definitely, like, we'll mention that one point. It's a little odd. Okay, as promised, here's our QQ plot for the anglerfish example. So the idea is here, and here it shows as a dashed line. I want the points to roughly fit the line. So you see them here, they're doing pretty well. Even down here, this one's a little odd. Not enough to really cause any concern. So I'm going to say roughly normal. And this is one of those things, there's definitely lots of, if you search on Google, there's lots of, hey, what's normal, looking at QQ plots. Really practice is what tells. Someone else might look at this and say, no way, but it is roughly normal. 1 point off is usually not too much for concern. That's likely our oddball outlier. So looking at some more, this one, I would say this is roughly normal. The points, they roughly fit the line. So even if they go off just a little bit, that's not too much of a concern. I don't want it doing a pattern. Like I don't want it going like this. That would be bad. I don't want it just going off like that. Or if the points aren't even near the line, that's bad. So this one, I would say is good. This is some cause for concern. The fact that it's going off both ways and it's shaped like this, I would say no, not normal. As for the second one, I would say there's some issues. You've got some long tails here. So, I mean, it's kind of like, it's sort of normal, but it's a little too wide maybe. So I might, and that's just it. It's not just about, oh, it is normal, blah, blah, blah. Like say, hey, this is approximately normal because the points fit the line, or say, no, it looks like these, at the tails, that it kind of goes off of the line on both ends. That would be your justification. Okay, so now that we've looked at the assumptions, we want to determine, hey, is this model a good fit? Does knowing the average sea temperature help give us more information about what latitude the anglerfish was found? So here's our output. So looking here, T-stat, I'm going to focus on the line that goes with temperature. That's my explanatory variable. So T value, that's my T statistic here, 3.629. If I want to know my degrees of freedom, there they are, that 23 degrees of freedom. And p-value. So that'll be right here, 0.00141. So at this case, if I'm using a 0.05 significance level, I'm going to reject the null because that p-value is smaller. That is strong evidence that knowing the temperature, the average sea temperature, does give us additional information about what latitude we find that fish at. So my estimate for sigma, so if I want to know how much the response variable latitude varies on average for the population, I can estimate it with variability I see in my sample. So here, that's going to be right here, my residual standard error here. So 0.4734. My confident, so this is, remember by default, you can even double check. It doesn't say what level. This is a 95 because if I take 97.5 minus 2.5, I get 95. So if I want my confidence interval for beta 1, so remember this goes with beta 0, beta 1. If I want to estimate the slope coefficient that goes with temperature, I am just going to go with this right here. And for this, we won't be using this. I'm going to just go to 4 spots, 1.2843. So my 95% confidence interval for beta 1, the slope coefficient associated with temperature, is going to be 0.3517 to 1.2843. So not only did we conclude that knowing temperature gave us additional information, we concluded that the temperature, knowing for each additional degree Celsius, we're seeing some sort of increase because this entire interval is positive. So things to note, we did have this outlier. We weren't able to figure out why, what was going on, if it was an error. So we want to determine, is it influential with and without? Like, if I exclude this outlier, is it drastically changing up my output? No, just because it is doesn't mean I can remove it. So I went ahead, I reported both. So without my outlier, I get y hat equal to 52.45 plus 0.82x. Remember to label what y hat and x are. Without, so this second dashed line, 51.26 plus 0.98x. It does look fairly similar. Note the main thing, you will have a degree of freedom change here. So without the outlier, it does look like, yes, this model fits better. So there's not a really good reason though to remove this point. Just because it would make everything fit better in itself is not a good enough reason. Oops, I thought there was some type there. So it might be worth reporting both. At least definitely you're going to report with the outlier. It definitely needs to be reported. So prediction. So remember, this is when I say, okay, I want to predict when sea temperature is 7.4 degrees Celsius, the confidence interval for the latitude, so the average latitude of all white anglerfish. So this is a confidence interval for when x is equal to 7.4 degrees Celsius. It's estimated to be between, I'm going to focus on this confidence interval, so between 58.16 degrees, because latitude's in degrees, as far as I know, and 58.85 degrees, with a point estimate of 58.51. That's what this fit is. This fitted value, that's our point estimate. Our point estimate is going to be the same for the prediction interval when we're still using x equal to 7.4. So remember our prediction interval, it's when we want to predict the latitude of a single new white anglerfish. So suppose one isn't in the day set and we just add one new fish that the average winter sea temperature is 7.4 degrees Celsius. We want to predict where that individual fish might be somewhere. In here, so we're looking for this outer one here. So anywhere from 57.47 degrees to 59.54 degrees with a point estimate of 58.51 degrees. So things to note, the prediction interval will always be wider than the confidence interval. Always. And we love to do that too. You might even notice on the data analysis 8, we definitely love saying, oh, well, here are two intervals. Which one is which? We love to do that. And that's how you know. So final conclusions. This is included on your slides. Obviously, please don't race to write all this. But so this is where we go back, answer all the questions. So the relationship, so describing the relationship here between average sea temperature and the anglerfish looks to be moderately strong with a correlation of 0.6. As sea temperature increases, the latitude of the anglerfish also tends to increase. We have here the model. So notice I didn't use y hat and x. I went ahead and I even wrote latitude and average sea temperature. That is allowed as well. You must have the hat though. We will freak out if you don't include the hat. Because if you don't include the hat, it implies it's the population line. And we don't have access to all anglerfish. So here, we reject the null hypothesis at a significance level of 0.05. Here, we give the t statistic, we give the degrees of freedom and the p-value. We do say, hey, there is very strong evidence that knowing the average winter sea temperature of the North Sea, that is a significant predictor. And here, this is where we're interpreting the slope here. So the data support the assumptions that increasing sea temperature may increase higher latitude of the fish with each 1 degree increase in average sea temperature. The latitude of white anglerfish is also expected to increase about 0.82 degrees. Note we didn't actually conclude in context the 95% confidence interval for the slope coefficient, although we should. So from our from our model, we can predict the average latitude for an average sea temperature of 7.4 degrees to be, there's our point estimate. And here, confidence interval, prediction interval, know that earlier we gave much more thorough examples of how we would write both of those intervals up. This alone wouldn't be a sufficient two-part conclusion for the confidence in the prediction intervals. And then this is talking about that outlier. Definitely feel free to look that over. We included this in the slides. And give your turn example to try.